Hello everyone and welcome to this video. I'm Raghad Jbaihi and today we're talking about the mutex mutual exclusion. Okay, firstly, software-based mutual exclusion. Software approach to mutual exclusion are designed for concurrent process running on either single processor or multiple processor a system that share main memory. This method typically rely on a basic assumption memory as access is mutually exclusive at hardware level. In other words, when multiple processes attempt to read from or write to the same memory location simultaneously, a memory arbiter ensures that the access are handled one at a time. However, the order in which access is granted is not predetermined aside from this fundamental memory level control. No additional support from the hardware and the OS or programming the language is required. Okay, so what is the mutex? What a mutex is, explaining its role in process synchronization. A mutex, short for mutual exclusion, is a synchronization primitive used to manage access to shared resource in concurrent programming environments. Its primary purpose is to ensure that only one process or thread can access a critical section, a portion of code that manipulates shared data at any given time. This prevents race condition where multiple processes attempt to read or modify shared data simultaneously, leading to inconsistent or unpredictable results. Okay, so how to prevent race condition when multiple threads access shared resource correctly? Okay, so a mutex is a synchronization tool used to prevent race condition by ensuring that only one thread at a time can access a shared resource. Okay, so how a mutex works. First, looking at the mutex. Before a thread can access a shared resource or enter a critical section, it must first look the mutex. If another thread has already looked it, the requesting thread must wait until the mutex becomes available. Exclusive access. Okay, so when a thread successfully looks the mutex, it gains exclusive control over the shared resources. Okay, and other threads are blocked from accessing the same resource until the mutex is released. Okay, and unlocking the mutex. Once the thread completes its task, it's unlock the mutex. This allows another waiting thread to accrue the mutex and safely access the resources. Okay, by controlling X row, his locking mechanism, mutex ensure that the mutex ensure that threads don't access shared resources simultaneously. This effectively prevents race condition, which can occur when multiple threads attempt to read or write shared data at the same time, leading to errors and unpredictable behavior. Okay, so the mutex provide a simple yet powerful way to ensure that shared data is accessed in safe, controlled, and consistent manner, helping maintain the reliability and correctness of concurrent programs. Okay, so the briefly compare mutex with related synchronization mechanisms such as semaphores and spin looks, highlighting key difference in behavior and use cases. First, the mutexes. So the purpose of the mutexes ensures mutual exclusion for threads accessing shared resource. Its value binary locked or unlocked. Ownership, only the thread that looks the mutex can unlock it. Looking behavior Blocking behavior. If a mutex is already locked, the requesting thread is blocked. Okay, so put to sleep until it's available. Its use case suitable for user space or kernel space synchronization where sleeping is allowed. Okay, so the semaphores, its purpose, general purpose, synchronization for signaling and controlling access to the resources. Okay, its value integer can be more when for counting semaphores. Ownership, no strict ownership. Any thread can signal increment or weight decrement. Has blocking behavior. Threads may block if the semaphore value is zero for weight operation. Its use case useful for resource counting, producer consumer problems, or coordinating multiple threads or processes. Okay, so the spin locks, its purpose, mutual exclusion like a mutex, but without putting the threads to sleep. Value, binary locked or unlocked. Ownership, only the thread that occur the locks should release it. Blocking a behavior, a thread trying to occur the lock actively waits, spins in a loop until it becomes available. Use case ideal for short critical section in a multiple processor systems where context switching overhead is higher than busy waiting. Okay. Here are some the key differences between it. Okay, so the mutex are needed for basic mutual exclusion. Semaphores offer more flexible signaling mechanism for complex coordination, and spinlocks provide fast looking and performance critical, low latency scenarios where threads don't need to sleep. Okay, so in real world analoging that help illustrate the concept of mutual exclusion in practical, relatable ways. Okay, first, I was talking about signal ATM machine. Imagine a bank with one ATM and of a line of people waiting to use it. Only one person can use the ATM at a time. Other must wait their turn. Okay, so they're using the ATM, a thread entering the critical section, waiting in the line, threads being blocked or queued, finishing the transaction. Thread release the mutex allow the next one to process. So just as the ATM avoids serving multiple people at once, a mutex ensures only one thread access the shared resource at a time. Okay. Shared print, another example about the mutexes. Shared printer queue in an office, multiple employees and print jobs to a shared printer. If everyone tries to print at the same time without coordination, pairs get mixed up. So a print service handle one a job at a time, like Mutex is allowing one thread into that a critical section. Other print requests wait in a queue, just like threads waiting for the mutex. So the print analogin shows how mutexes prevent output conflict and ensure orderly access to shared devices. Okay, here are some example about that. Okay, so the flowed counter without mutex. Okay, I create two threads that both try to increment a shared counter. Since there is no control over how the threads access the variable, they might both read and write at the same time. This causes a race condition, which lead a wrong final result. For example, instead of getting 200,000, the output might be much lower. Okay, here are code in PCD code, yeah. And okay, and to fix the problem, I use the mutex metal exclusion. Mutex makes sure that only one thread can access the counter at a time. Okay, so this way the threads take turn updating the counter, and the final value is always correct. Okay, so this is a simple and safe way to avoid race condition. Okay, here are the correct counter using mutexes in BC code. Yeah. Okay, so I now I'm talking about what can go wrong with mutexes. First, deadlock. This happens when two threads are both waiting for each other to release a lock. Okay. Secondly, priority inversion. This can happen when a low priority thread holds a lock that a high priority thread needs. The high priority thread gets stuck waiting, which defeats the purpose of priorities. One way to solve this is to use something called priority inheritance. Third, a fairness issue. Sometimes one thread might keep getting the look over and over, and other don't get a chance. So this is called starvation. Some system offer fair looks for scheduling policies that make sure all threads get a turn. Okay, samurai. So, the using threads and to increment a shared count can be tricky if you don't use proper synchronization with data mutex. Threads can mess up the results with a mutex things work correctly, but you still have to be careful. Okay, so the problem like deadlock, starvation, a priority issue can happen if mutexes are used the wrong way. Learning how to prevent this problem is important when working with concurrent progress. Okay, here are some references about this report, and thank you everyone for watching.